Hello, everybody. Hey, this is going to be week 5, lecture 3, which is going to be on friction and its application to primarily Newton's second law and free body diagrams, etc. So again, this is Thursday the 12th, and I am going to probably ignore here and talk to the students out there. So here we go. All right, ladies and gentlemen, what the heck is friction? What is friction? All right, everyone knows what friction is, right? Anyone, give me just an idea of what you think friction is. Yes, sir.
It's like the surface is has resistance to stuff moving over it.
Excellent. The surfaces, and that's really going to be a key. When you have the surfaces between two things, there's going to be a resistance to move. That's really good. Anything else? All right. That really is kind of a key, but let's kind of go ahead and put a definition on something. Friction is an oppositional force that will point in the direction opposite to the motion or okay, so friction is a oppositional force that will point in the direction opposite to the motion or potential motion. So if I am on an inclined plane and it's super icy, right, and I happen to not be moving, okay, there's just enough friction to keep me there, okay. But I'm going to potentially, if I'm going to move, I'm going to slide down the ramp, okay. If I just move right, then I'll probably start sliding down, okay. So there's motion and potential motion, which is essentially two different kinds of friction, which we will talk about here momentarily. All right, let's see if we have it. If we look, okay, and what we're going to do is if we have, for example, a block kind of on a surface, let's kind of make our surface blue, okay? And if we're going to apply a force here, right? Now, it might not be moving, okay? So the force of friction is going to be going to the left, whether it's moving or whether it's not moving, okay? Now, if the applied force is greater than the frictional force, then it will start to move. And if once it's moving, then it's going to accelerate. And let's go ahead and look. If we kind of take this part right here, we'll take this part right here, and we're going to blow it up. Like if we magnified it a gazillion times, okay, then what we would see on the bottom of the block, we would see this sort of uneven surface, right? We would see this uneven surface. And at the same time, we would have the ground. The ground would also have a uneven surface, right? So if I use my two hands here, and here are all the irregularities of the block, and here are all the irregularities of the ground. Okay, so they kind of intermesh to a certain degree. So as we push here, there's going to be a resistance to that motion between those two surfaces. Okay, and we can have various levels. We can have various levels of the amount of friction, which is essentially due to how much interlocking that they have, All right, so if we kind of push at a certain point, it is going to essentially rise up and move, okay? And when they move, then essentially it's only going to be the tops of the little irregularities that are going to move past one another. Okay, if you've ever ridden a skateboard and all of a sudden you suddenly come up on a rough surface, okay, then you can often still make it, right, without your skateboard stopping, but now your skateboard's kind of hitting the tops of those bumps. And if you slow down enough, then it might go down and kind of sink into a lower one and then kind of stop, and then you will go flying, okay? So part of it has to do with how much irregularities there are. And if we have these irregularities and we have a bigger force, okay, so if we have, for example, the force of gravity that's pushing down, okay, that means the normal force is pushing up, okay? And we talked about normal force in week 5, lecture 2, okay? So if we're pushing those two surfaces together more, okay, then there's going to be a greater amount of friction. So the force of friction is proportional to the normal force. So whatever sort of surface interaction that we have, okay, if we push them together more, then the friction is going to go up. So the force of friction divided by the force normal is equal to what is called mu. Okay, this is the Greek letter mu, and it is called the coefficient of friction. Okay, the coefficient of friction. And it's usually between 0 and 1. Okay, it is usually between 0 and 1. There are some examples where the coefficient of friction is greater than 1, okay, but it's not very common, and it's usually when it comes to rubber, okay, so you can get rubber tires that are squishy enough and yet strong enough to intermesh with either concrete or asphalt, so that you can get a much greater grip, and that would give you a coefficient of friction that would be greater than 1. But normally we're not going to see, except maybe for a question. Yes, sir.
So with friction, how does it work when so in the case of asphalt,
Yes.
you can't. It prevents you from moving forward, but it doesn't push you backward. But with something like slippery like ice, you can't. It doesn't really stop you from moving forward, but it'll make you move backwards.
That's probably not exactly right. In the same way that if you're on let's say asphalt, let's say with rubber soled shoes, right? So that rubber tends to be a good grip, but it's always the combination of two surfaces. Okay, so if we take rubber on asphalt or concrete, then that coefficient of friction is going to be higher. So as you said, okay, if I try to go forward, it can kind of prevent me, but it's not going to make me go backwards. So a force of friction in and of itself does not make an object go forward. Okay. Now there is kind of a little bit of a trick to that. Okay. Now, for example, if I want to walk forward, and I'll get back to the ice here in a second. If I want to walk forward, okay, I am pushing backwards, right? I am pushing backwards. So if I'm pushing backwards, how am I going forwards? Okay, if I push backwards, let's say here is my foot, okay? Now my applied force is backwards, yet velocity is going to go forward. How is that possible? What is pushing me forward? What is pushing me forward? And as you might have expected, it's going to be the force of friction, okay? So there's going to be a force of friction, okay, here. Now, this is actually going to be static friction, which we'll talk about momentarily. And static friction is where it's preventing potential. It's preventing potential motion, all right? Now, so basically these two things are going to be equal and opposite according to Newton's third law. Okay, now the result, as we've talked about a little bit, and you probably investigated, the forces are the same. The result of the forces are different. Okay, so I applied this, and this force, the static force of friction, is never going to be greater. It's never going to be greater than this, but essentially, the friction translates this force from my foot to make me go forward, okay? Now, if we lower, as in the case of ice, when we lower the coefficient of friction, make it really slippery, and just to give you an idea here, ice on ice has a coefficient of friction of 0.1 for static friction. Once it starts sliding, it's 0.03. Rubber on dry concrete is 1. So rubber on concrete, and asphalt's going to be similar. Wood on wood, 0.4. Steel on steel, when it's unlubricated, 0.7. So in the case of two different surfaces and you have a problem, okay, I'm either going to give you and tell you what the coefficient of friction is between those two surfaces, or I'll give you everything else and you're going to figure it out. Okay, but back to the ice. Okay, so if I can apply a force here backwards, that becomes greater than this static friction. And what's going to happen is now it's going to slip. Okay, so now it's going to slip. So when this force applied is greater than this force of friction static, okay, then my foot's going to slip. Okay, now if we think about moving, let's say on ice, and you probably had this, you could essentially start to kind of move and almost run if you have good enough balance, but you're not going to move anywhere. Okay, you're not going to move anywhere because now there's no friction once you start sliding to make you go forward. Sometimes it can feel like you're going backwards. Okay, because as you lose your balance, you might stick your foot out this way and all of a sudden you fall backwards. But that has a lot more to do with where your center of mass is and the rotational part. Okay. All right. So as I've hinted here, there are two types of friction. There is moving friction. There's non-moving friction. Okay. And that right there, static friction. Prevents motion. Okay. And it is going to have a coefficient of friction with a little s like that, which means static friction. So kinetic friction is going to slow motion down. Okay, so it's always going to working against that motion, right? And that is going to have a coefficient of kinetic friction. So that little k there indicates moving friction. All right. So now when we compare those two, static friction, okay, is always greater than or equal to kinetic friction. Now, as you guys can imagine, okay, if we have two really rough surfaces, then the friction is going to be greater. As in with wood, if we start using sandpaper or some sort of smoothing device, then the friction is going to get less and less and less. Okay, so there can be a situation where the static friction and the kinetic friction are actually equal. And that's very often when there is a lubricant, like between steel and steel. But if we have a lubricant in there that allows them to slide pretty easily back and forth, then the static friction can equal the kinetic friction. I'm just looking right here to see if I can find it on my little Teflon on Teflon. So if we have two Teflon surfaces, obviously really slippery, okay, then the kinetic friction and the static friction are the same. Okay, so it essentially acts as sort of a lubricant there. Lubricant in ball bearings, 0.01 and 0.01. So when you have that situation, these two things can kind of be equal. Okay, but for the most part, when you're studying this, usually it is going to be a different sort of thing. In today's question of the day on 11.2, okay, you're going to start like the question of the day on 11.10. You're going to start with a block on a ramp, right? So you can have a block on a ramp and you can get it just to not move, right? And usually, as in the case between static and kinetic, if we just give it a little bit of a push, then it'll start sliding, okay? And that example there is probably the best example of the difference between static friction and kinetic friction. So once you kind of just get it going, okay, then it's going to continue. And if you guys have ever pushed a heavy box across, let's say, a garage floor is probably the best example. You start pushing and pushing and pushing, and it's resisting, and all of a sudden you just feel it release. And when it releases like that, it's usually easier to keep it going as you push it. So once you get it going, then you can kind of move it fairly or easier, depending on how heavy it is. Okay. All right. So now we're going to kind of go from here, and we're going to see how these sort of questions play out. So the force of friction is equal to mu force normal. The force of friction is equal to mu force normal. Okay? So very often, and I've done this in the past, and it's a little bit funnier. It's a little bit funnier in a class where everyone's showing up every day. And I'll say, when I say force of friction, you say mu force normal. Force of friction, mu force normal. So it's kind of one of those little things that if you get it in your head, all of a sudden you go friction, oh, mu force normal, friction, mu force normal. And that is a little trigger in your head to kind of give you one of those, oh, I know one more thing. And that can go along with the kinetic equations. And in this question of the day for the 10th and the 12th, at the very end, I'm going to ask you something about what is the velocity? What is the velocity after you calculate the acceleration due to either friction or the applied force or gravity? Okay. So what I'm about to do is I'm going to give you a couple of examples here that will kind of show you how this whole thing works. And some of that is modeling how to draw a free body diagram. So I'm going to be repeating things in this lecture that I went over on week 5, lecture 2. Okay. All right. So let's take a look at this, and let's do a pretty simple example. Okay. So let's have a 5 kilogram object. Okay. And we're going to have a coefficient of static friction that's equal to 0.8. And I want to know how much force is required to get that object moving. Okay? So, question number 1. How much applied force is needed to move the object? Okay, so that is our first question. So what we want to do, first thing is we want to draw a picture, and that was not in my description the other day, although I did talk about it. We have our picture. Okay, now we want to draw a free body diagram. So the first step in drawing a free body diagram is making a convenient XY coordinate system. Now our convenient XY coordinate system is just going to be our standard X and Y. Okay, and in that lecture I said you might want to change your normal axis of rotation, okay, to make it easy. And that usually when you have an inclined plane like here, you're going to want to make your X in the direction that the object will slide or potentially slide. And that makes, by doing this, it makes things a lot easier. Okay. Now with this, obviously, if it's going to move, left and right. It gives us our X and our Y. All right. So now we want to draw, okay, step number 2, draw a force vector for everything that touches an object plus gravity plus friction. Everything that touches an object plus gravity plus friction. What is touching? What is touching this object?
The ground.
The ground. And the ground is going to be pushing up, okay? And what is the force called of the surface pushing on an object? And that's the normal force. And I'm going to say this normal force is F sub n. F sub n. And what else is going to be touching this object? And it might be a little bit too obvious, okay? But we're going to have an applied force. We're going to push. We're going to push on this block until it moves. And this is what we're trying to find out. Okay. Now, everything that touches it, which was the ground and our applied force, plus gravity. So as we all know, we're going to have the force of gravity is going straight down. Okay. And that force of gravity is also known as weight. And we know that from the lecture the other day is going to be your mass times the acceleration due to gravity. And on the surface of the Earth, that G, as you know, is 9.8. All right, and then the last thing that we have here is friction. Everything that touches it plus gravity plus friction. And the friction, now if we're pushing from left to right, then the friction is going to be potentially going this way. All right. Now, I kind of purposely put these two kind of in the wrong spot. Okay. So what we should really do, okay, and again, you can do exactly this. All right. But a free body diagram technically is just talking about the forces, okay? And I believe in step number 3 in there, we're going to use a dot. We're going to use a dot to represent that whole mass, okay? Now with the block, it's pretty straightforward, okay? Now, as we will go over later, this right here would be at the center of mass. Again, we haven't talked about center of mass. That has going to have more to do with when things rotate. Do you have a question? Okay. So now we're going to draw all of our arrows. So we're going to have the normal force going up, the force of gravity going down, and the force applied going to the right, and the force of friction, static, is going to the left. So all of the arrows are emanating from the mass. Okay. Now, we can certainly transfer this and put it right on top. You can put it right on top of our picture there. And for simple things like this, that would be fine. But very often we want to kind of look at the overall things when we're just talking about the forces. So, because I might have distance in here, and I might have other things like there could be an angle and whatnot. And I am going to kind of shift here so I don't run out of room. We are now going to solve, this equation. So the next step in the drawing a free body diagram is to resolve all of our force vectors into our x and y. Okay. Well, all of these are either going in the x and the y, so we don't have to change them because they're already there. Usually when you have an angle like I just erased is when you're going to have to change some of those vectors into the x and y. All right. So now we're going to use Newton's second law and say the sum of the forces in the y is equal to ma. Okay. Now, in my first question is how much applied force is needed to move the object. Okay. So now I'm going to kind of change this and say this is y, sorry. The sum of the forces in the x is going to give us that. All right. So what two forces are going up and down?
Normal force and gravity.
Normal force and gravity. Which one's positive?
Normal force.
Normal force. Now, technically we could say down is positive, but it makes a little more sense. So we're going to say the normal force minus the force of gravity is going to equal to ma. Okay, but in this one, what's usually going to happen, if we think about a block on the ground, okay, it's not going to sink. It's not going to sink into the ground. At the same time, it's not going to levitate. It's not going to levitate off the ground. So we know in the y direction, there is no acceleration, okay? And that means that this is going to be equal to 0. So the normal force minus the force of gravity is equal to 0. Therefore, we're going to take this negative f of g and bring it to the other side. So the normal force is equal to the force of gravity, which in this case, mg is going to equal to 5 times 9.8. And 5 times 9.8 is going to give us 49, okay? So 5 times 9.8, 49. So our normal force is 49 newtons, okay? So now we're going to say the sum of the forces in the x is equal to ma. And as I was starting to say, because I got out of order there, now in order for this to move, okay, my applied force has got to be greater than, it has to be greater than the frictional force, okay? So this applied force minus the force of friction has got to be greater than ma. It's got to be greater than ma. Now, I suppose, and it does have to be greater in order to get it moving, okay? But we're essentially going to use an equal sign there, and then see that it's just going to be above that. Okay, so now, you know what? This just has to be greater than 0, right? Okay, so it just has to be greater than 0, and therefore we can say that the applied force has to be greater than the force of friction, and we know that the force of friction is equal to mu force normal, okay? Force of friction is equal to mu force normal, and we know that our coefficient of friction is 0.8. So we can say 0.8, our normal force is 49, and 0.8 times 49 is going to be 0.392 or 39.2. Okay, so our applied force has to be greater than 39.2 newtons. All right, so 39.2, the applied force has to be greater than 39.2. All right, so this would be another sort of question. We are going to have an applied force of 30 newtons, applied force of 30 newtons on this 5 kilogram object. What is the acceleration? What is the acceleration of the block? And the answer is 0, because we just determined that it has to be at least 39.2. So if I said 30, okay, then the answer would be 0 because the applied force was not great enough. Okay, so let's get to a second question here. And I'm going to kind of erase some of this when I go to do this. So we're going to say question 2, if the applied force is equal to 50 newtons, okay, what is its acceleration? Okay, now we already know from what we talked about, is the coefficient of friction, static friction, is 0.8. Okay, but as long as we're greater than 39.2, that object's going to move. Okay, so we're going to need to know what the kinetic friction is. So let's say the kinetic friction is 0.6. So now we're going to go through this whole thing again, except our normal force, this part right here, is going to stay the same. This part right here, the normal force is still going to be 49. All right? So all we're going to do is we're going to change this one down here. So now we're going to have an applied force minus the force of friction, and now that is equal to MA. Okay, it's not just greater than 0. Okay, so now we're going to have 50 minus our mu, which is 0.6, times our normal force, which is 49. And that's going to equal to 5A. That's going to equal to our mass of 5A. So 0.6 times 49 is going to be, what, 29.4? Okay, so we're going to say 50 minus 29.4. This whole thing divided by 5 is going to be our acceleration. So 50 minus 29.5 is about 20. Divided by 5 is going to be about 4, I think. So I'm just going to double check a couple things here. 0.6 times 49 is 27.6. Messed that up. 27.6. And now we're going to have 50 minus 27.6 is 22.4. Divided by 5 is going to be 4.48. Okay, so our acceleration is going to be we'll call it 4.5. So that is essentially how you're going to do those sorts of equations. Now, from here, I could say, if we push at that 50, how fast is the object? How fast is the object going to be moving after we push it for 2 meters? Okay? If it started at rest, we know the acceleration and we know 2 meters. We're going to have 3 variables. Okay, so then we can go back to those kinetic equations, and that would be equation number 4. V final squared is equal to V initial squared plus 2AD. Initial velocity would be 0. So we take the square root of 2 times the distance. I said 2, that's 4, times the acceleration, which is 4.5, which would be 18. Then we take the square root of 18. That's going to be a little over 4. So the velocity would be something like 4.2. Okay, I could say, how long does it take? How long does it take for it to go those 2 meters? So now, since I know the final velocity, let's call it 4.2, I know the initial velocity is 0, I can divide that by 4.5, and I'm going to get something a little bit less than 1 second. Or I could just use displacement is equal to VIT plus 1/2 AT squared and solve for T. So all of those things are kind of in play. But what's really new here is all of this friction here. So where it gets a little tricky is when you have an inclined plane, And I'm going to kind of show you here, because it's a little bit trickier. I'm going to set up a free body diagram for a inclined plane. And I think that I did this in week 5, lecture 2, when I talked about free body diagrams, but I'm going to do it again because it's applicable. It is applicable to question of the day for 11.2, your problem set number 2, and today's 11.12 question of the day. And then there's going to be a problem set 3, which is going to be dealing with this. Okay, so let's just say we have an inclined plane, and let's say it is 30 degrees, okay? And we're going to have a 1 kilogram block, And we're going to have a coefficient of friction that's equal to, let's say, 0.5. Now, it could either be kinetic or static depending on the situation, but given the time, I'm just going to kind of set this up. All right, so now we want step number 1 in drawing yeah, go ahead.
Is it 30 or 30?
30 degrees. I kind of messed it up. 30. My degrees is a little error. I usually make them too big. So then it looks like 300 or 38 or something. Okay, 30 degrees. All right, so step number 1, draw a convenient XY coordinate system. And in this case, as we kind of pointed out, we want the X to be going in the direction that it is going to slide potentially. Okay, so that's going to be our X, and that's going to be our Y. Okay, now we're going to draw, and I'm going to do it separately here, although we could do it directly on our little picture there. Everything that touches it, plus gravity, plus friction. Well, the only thing that's touching it is our normal force. The only thing that's touching it is our normal force. Okay, plus gravity. Gravity is always going to be going straight down. And then plus friction. And if there's friction, it's going to be going up the ramp. It's going to be going up the ramp. Okay, so that right there is our free body diagram for this, right? But to really make this useful in solving, for example, does the object move? Okay, well, if the object moves, this would be static friction. If it is moving, okay, then what is the acceleration down the ramp? And in which case that would be static friction, okay? But the key here is that we want to, and this is step number 4, resolve the vectors that are not going in the XY direction, okay? And that's going to be gravity. Gravity is not going in either the X or the Y. So we're going to take this and we're going to break it into this vector there and that vector there, okay? Now, it's probably a little bit easier to see if we put this vector right there. So we know that we're going to break it up using trig. So that is going to be a right angle because we're going to have X and Y, okay? And I'm going to draw it right here, okay? So if this angle right here is 30 degrees, then this angle right here is 60 degrees, and now we're going to come normal, but into it, okay? And this triangle right here is the same triangle there. So we now know that this is 90, this is 60 degrees, and that's 30 degrees. So this angle right there is 30 degrees, okay? So we know that this f of g is going to be 1 times 9.8. mg is our weight. So if we want to do this one, our force of gravity in the y direction, is going to be cosine 30 times 9.8. Cosine 30 times 9.8, which is going to be probably about 8.6. Okay, I'm just going to say it's 8.6. I think the calculator will tell you that. So this is going to be 8.6. And the force of gravity in the x direction, which would be down the ramp, is going to be sine of 30 degrees times 9.8, which is going to be 4.9. 4.9. Okay, so if that is the case, okay, then the force of friction is equal to mu force normal. Our coefficient of friction is equal to 0.5. Our normal force is 8.6. And 8.6 times 0.5 is going to be 4.3. Okay, so that means that force of friction, okay, is going to be less going up than it is going to be coming down. Okay, so it would be sliding down the ramp. All right, now, again, we kind of made this a little more generic and did not distinguish between kinetic or static. So let's say if it's both, if they're equal to each other, then the acceleration is going to, sum of the forces in the x is going to equal to ma. We're going to have 4.6 down the ramp minus 4.3 up the ramp is going to equal to 1 times a. 4.6 minus 4.3 is 0.3 divided by 1. And then our acceleration would be 0.3. Now, I could then ask you a bunch of kinematic stuff about that. Okay, but that's essentially the gist of when it gets a little bit trickier, when we're on an angle. And the question of the day for 11-12 is very similar to dealing with all of this stuff. And I'm going to ask you about the static friction and kinetic friction and whether it's going to move, etc. Okay. All right. So hopefully this is going to help you out, and you're going to see more applications of this in week 5 problem set 3. All right. We'll see you next time.